next problem is called merge two binary trees. We are given two binary trees, root 1 and root 2. Imagine that when you put one of them to cover the other, some nodes of two trees are overlapped while the others not. You need to merge two trees in a new binary tree. The merge rule is that if two nodes overlap, then the sum node values up as the new value of the merged node. Otherwise, the not node node will be used as a node of the new tree. Return the merged tree. And also the merger process must start from the root nodes of both trees. So for example, here we have 1 and 2 and they add up to 3. We have 3 and 1, they add up to 4. 2 and 3, they add up to 5. And then we have some standalone, not overlapping nodes. For example, 7 will be just mapped here. 4 will be mapped here because we have nothing here in the first tree. But in the second tree, we don't have a left child or the second level node, but in the first tree we have it, so we just map it here. To solve basically the problem, we will recursively build up the tree using the root 1 and root 2. So we'll start by declaring a new root of the merge tree, and we will pass it to our helper function. That helper function will also return the whole tree after it has been built. We will recursively build it by passing the root 1, root 2, and also the new root that indicates the new merged tree. For the helper function, we will have a base case because we will be calling it recursively. We will check if any of the roots are null, and if they are, we will just return the one that's not null. So basically, those are non-overlapping roots that we had, non-overlapping nodes that we had in the example 1. That's the base case. In the standard case, we will just add the values of the overlapping nodes to make the value of the new root, and then we will recursively build the left subtree by just passing the left subtree of root 1 and root 2, and also the new node that will represent the left subtree of our new merged tree. The same goes for the right subtree, and we also just return the root after it has been built. If you don't count the number of nodes that are needed for us to return and create a new merge tree, the space complexity will be the stack, the size of the stack of the smaller of the tree. So the number of nodes of the smaller subtree, because we are returning early, we have this break on the line 23. The time complexity will be again the same. It will correspond to the number of nodes in the small subtree because we are short circuiting. We are returning early